Ladies and gentlemen, welcome to machine learning. In this video, we will be talking about the influence of the training data size regarding our model's ability to generalize and about the model complexity and how that influences our our model. So in the last videos, we talked about the bias-variance trade-off. So again, just to summarize, what is the bias, what is the variance? So the bias is how much we're actually missing. Or for example, if we have a low bias, we have a grouping that is fairly in the center. And if we have a high bias and low variance, we are constantly hitting not the center, but slightly to the right. If we have a high variance, we have a very large grouping. In case of a low bias, we're actually closely to the center. But if we have a high bias and high variance, we're off to the center and have a large grouping. So how does model complexity play into that? So if we increase model complexity, like we talked about in the last videos, we will decrease our bias because our bias is how much we're missing by a constant. So how much we're missing. And this is dependent on the model complexity. So if we have a complex model, we can say that we have a lower bias. But the problem is that as soon as we are introducing more complexity into the model, we will give it more ability to learn the random noise of that data. And that increases our variance. And then again, because we not only have the bias variance, we also have a noise term. So this is our irreducible error in our expected loss, and it will always be there regardless of what we do. So you might say, well, we just need to increase the complexity, but then we also increase the variance. If we lower the complexity, we will increase the bias because our model is not complex enough to find the underlying structure of our data. So there is this one sweet spot where we are not in the underfitting regime that looks, for example, like this. So this is our data, and we plot something like this. This is underfitting. And the overfitting regime is where we have data points and we go through each data point. So there is this sweet spot that we need to find regarding model complexity. We can say that, well, how does the training data actually influence our problem? So let's say we have the influence of our data, and this is a very, very simple model. So we have a high bias by default. And we see that if we have a simple model, we are able to reduce the variance almost to zero. So our actual error, so the expected loss, is here because we also have that irreducible component. So more data will change our variance, but never our bias. So in a complex model, we have a low bias by definition, because we're capable of learning the parameters of the underlying structure of our data, but we're more influenced by the variance. So we have a very, very high variance, and we need significantly more data to get the error close to our constant bias that we can't remove with our training data size. So the bias term, to summarize, cannot be influenced by the training data. And increasing the training data will reduce only the variance. So in the infinite case, we will have an error that is just made up of the irreducible component and our bias. So what is the performance in practice? Well, we had our expected loss over our data, and this is something we cannot compute. But what we can compute is our training loss. So after we train our model, we can then use those values those x and y points. So we had x and y points, and compute the loss of those. So the difference. So we had y predicted, pred minus y true, for example, squared, and we average those over the number of trainings point we had. So y and n is part of our data. And we see that, for example, and what we see is that our training loss can be actually very, very small. But it's not true that we cannot say that the training error is equal to our expected loss. Let's go all the way back to this image. So in this case, we have overfitting. So our training error is actually 0 because our model is able to fit to the data perfectly. But if we now have another data point that was not in the training, we see that we have a very, very large difference between the predicted value and the actual true value. So this is why we cannot use the training error on as our expected loss. So our training error is always smaller than the expected loss, because it can be that our training error is 0, but if we then try it on some new data, our training or our error is very, very large. So what can we say? Well, how can we approximate our training error, our actual expected loss? So we can say that our expected loss is the error on a training set, on a test set. So we have all the data, we shuffle it randomly, just in case there is some order to it. And then we use one part to train our model and one part to test our model. So for example, in the worst case scenario, the training error will be E train is equal almost to 0, and E test, so the testing on the data, will be infinite or very, very large. But we can say that in this case, we are in the overfitting regime because our training error is 0, but our validation or testing error is very, very large. So the average test error will be equal or approximately equal to our expected loss. And our test error is again the xt and yt from a data set that is only used for testing. We average over all elements where we compute the loss. It's very important to understand that we are not using this part to estimate our parameters w. So we're only using this part, and this part is for testing only. So if we now look at the test and train error, we see that with increasing model complexity, so we have a fixed amount of data, we used one for test and one for train. We see that if we increase our model complexity, our training error will go down, down, down. This is because we have, with a complex model, we reduce the bias, but we will get a higher variance. So this is the variance difference. This is the variance. So the variance is the difference between the train error and the test error, because here we have a low bias, but a high variance. So this is why we have a big test error. If we have a very, very simple model, we have a low variance, but a very high bias. So here we have the error is because of our high bias. So again, for a fixed set of data, there is a sweet spot for the model complexity where we have not underfitting and not overfitting, but we're actually hitting this sweet spot where our test error is minimal. And this is the point where we want to be. So we can just simply do that by increasing our model complexity over time, but this is a very, very tedious process because for every model complexity, we have to train our data. And this can take many, many, many iterations, and this is why it's not done like that. I hope this video gave you a better understanding regarding the expected loss in the training and test data set, and how the influence of data only influences our variance and not our bias, how we get what the bias actually is, and how our model complexity influences our bias and variance. If you have any questions regarding this topic, feel free to ask them in the comments down below. Otherwise, thank you very much for your attention, and I'll see you in the next video.